Welcome to my channel Paul Physics Classroom. In this episode we will study the wave equation. Mainly our aim is to convert our second order one-dimensional wave equation into a finite difference form and how to solve numerically. The basic understanding will be formed in this class. First, we consider a second order one-dimensional wave equation of this type: d2u some d22 some v square del square u del x2, where u as a function of x and t, space and time. Now where v is the speed of the wave, which is assumed to be constant here, and because it is a second order differential equation, you need two boundary conditions at least. These conditions, two initial conditions, first we discuss, that is ux0 at time t equals to 0 at for all space point which is ix, which is given, and the del u del t at t equals to 0 for all space point x, that is equals to gx, which are given for a particular problem. Now also we set the solid boundary conditions or dead wall boundary condition. That means here for the particular case at x equals to 0, at this point the u0 for all time which is 0, and other point u l comma t, that means other end, which is fixed forever. This sort of equation will arise in many situations in physics and engineering, or in physical sciences and engineering, including the waves on string. That means acoustic, any musical instrument can be explained with this equation. EM waves, sound waves, water waves, and many things. We will use mainly the language appropriate for here for waves on a string, but our method is generally applicable for all kinds of waves. First, we want to replace this equation in a finite difference form, which is a 3-point central difference approximation. If you do not know what is 3-point central difference approximation, you go through my earlier videos. That the link of that video will be given in the description, as well as here I button rather will be given. You go through, then after that you will study this episode. You will listen to this episode. d2u dt2 that is equals to ui t plus 1 later time, that is twice of ui t minus 1 divided by delta t square. Second order accurate approximation, as well as the space point. Here space points is I plus 1 I minus 1 at a given time. Similar thing here, t is changing, t plus 1 t minus 1, here I plus 1 I minus 1. That is the difference, but this is the same thing, the 3-point central difference approximation. We just replace or substitute this thing into our main equation 4.1, and after that we will get this equation. Very straightforward thing. We just substitute this, and after transposing and cleaning up all these things, you will get ui for any point, arbitrary point I, at t plus 1 at time instant, that will be twice of ui at time instant t minus ui t minus 1, that means before t time, and r square ui plus 1 t ui minus 1 t minus 2 ui t, where r is equals to v times delta t divided by delta x, which is called the coherent number, or this is coming from the stability criterion, and which is lesser or equals to 1 for this case. In later episode we will definitely discuss what is stability while solving finite difference method. And this method, now we are assuming this thing. This method is a 3-step because here are 3 time steps are involved: t minus 1, time step t, and t plus 1, that we want to know. And suppose we know all these things in the right hand side of the equation. Now there's another set of conditions are there. We need a starter equation, because at t equals to 0 this equation becomes u1, but here there comes ui minus 1. So that's why we need a starter equation. After starting, we'll use this 4.9 equation, and for that matter del u del t equals to gx. Let us use the second order accurate first derivative del u del t. That means ui at time say t equals to 1 and ui t minus 1, and because at t equals to 0, that means in one hand there is a t equals to 1 point, and in other hand that is t equals to minus 1. That is called the central difference approximation, that is ui1 minus ui minus 1 divided by 2 delta t, which is given g sum at point xi, at any point that is valid, all points on over the x-axis. Therefore from here we can say ui minus 1, that is equals to ui1 minus 2 delta t gxi, and we use this I am just rewriting this for 4.9 equation in this form. At t plus 1th level I t plus 1 and whole thing is there. The same thing is written here. Okay, I just transposing and collectively the t all the terms t time level is here, and t minus 1, and here t plus 1. At just as I said earlier, t equals to 0, here comes the u minus 1 term from here, and we just replace this thing. This term is replaced here, and we will get the starter equation. What is that? The starter equation becomes just you replace this thing, ui minus 1, whole thing is here, and you just replace this thing here, that you will get ui1 to delta t g xi. After just cleaning up, you will get ui at one level of time, that means t equals to 1 from t equals to 0. Because t equals to 0, all these quantities are known from the initial condition, and this is known from the given function. That means u1 time level 1 is known. This is called the starter equation. This is called the starter equation. On all the quantities of the right hand side is known, and using this equation we will get t equals to 1 level, and so for subsequent time level we will use the equation, this equation for this 4.1 equation or this equation. The both are same, 4.9. Use the 4.11 equation. Now use the 4.11 equation, and we will marching down the time step, and we will get all the values. If we use recursively for all points for I equals to from not 0 end is given, and x equals to l is known, so there it is fixed for all time instant. That means intermediate time step. For if you run for all the data points, you will get at t equals to 1 for all the data points. After that, getting all this value, we will get t equals to 2 level, t3, but we use this 4.11 equation, and we want to discuss further in graphical manner. That means this is our grid. It may not be a rectangular grid for all the time, but here it is drawing for simplicity. This is the grid along the x-axis, and this is the grid along the t-axis. And this all the filled black points are known from the boundary condition or initial conditions. This is known at t equals to 0 level. This is known. And from there we will go to the next grid points. This is a finite difference grid. Next grid point using this equation. This is our starter equation. We use this equation, and all the values here will be known after using this thing, and all these will be black dots after using this. And from this level to this level, we will jump from this level to this level. For all points, for all I, use that equation, ui t plus 1 r square, already discussed, which is basically 4.11 equation from time level 1 to 2. And for all points, we look through this and we will get. And this way we can solve the wave equation for all the grid points, and we can march down along the time axis for all points. And therefore we have solved this sort of wave equation. In the next episode we will study how to implement using Python.